So here we have an expression and we want to find the maximum value of it for x being a real number. Now I know we can take the derivative of this and then set it equal to 0, I know. However, we often want to think of more elegant solutions because sometimes the most practical solutions might not actually be the most practical. Sometimes the work might be very tedious and we want to avoid that path as much as possible. So how are we supposed to even do this question then? Well, we're going to be using a method that oftentimes actually produces very elegant solutions. It's called the AMGM inequality. I have a video about that, however, I'm also going to briefly explain it here. The AMGM inequality, written as AMGM, this inequality basically states that if we have two real numbers a, b, both non-negative, and by the way, this extends way beyond two numbers, but for now, I'm just going to cover the case for two numbers. So if we have two non-negative numbers, then the AMGM inequality tells us that the arithmetic mean of the two numbers, that is, their average basically, is always greater or equal to the geometric mean of the same two numbers. So that would be the square root of AB this time. So hence AM, arithmetic mean, GM, geometric mean, inequality. And this always holds as long as they're both non-negative. So how can we somehow use this to derive a maximum value for this expression? Well, we need to first consider a few things. Let's first consider the numerator, okay? If the numerator is negative, then there's no way we're actually going to be reaching maximum. Why? Because the denominator, as we see, is always positive for real x values. So if this is positive and this is negative, then we're going to get negative values. And by testing some x values, we can definitely see that there are positive values of this expression. So it's definitely not going to be maximum. Well, that must show that the top portion must be positive. But when is it positive? Well, we must either have x and this expression inside the brackets to be both positive or both negative. Well, if they're both positive, then it seems reasonable, right? However, if they're both negative, then is that even possible? Well, if x is negative, then this has to be negative. So let's see when that exactly happens. When does 3 to the x times x squared minus 4x become smaller than 0, where x is also negative? Well, then we can move the 4x over, so that's 3 to the x times x squared is smaller than 4x. And we can divide both sides by x, but x is negative, so don't forget to switch the signs. We would have 3 to the x times x is greater than 4. Hold up, 3 to the x is always positive for real numbers x. But if x is going to be negative, then there's no way that this expression is going to be greater than 4, because this side would be negative then. So there is actually no values of x such that, or there are no values of x such that both of these are actually negative. Therefore, the numerator, we conclude, must have these two terms both positive in order to reach maximum. Wait a minute, that was one of the main constraints of AMGM. If they're both non-negative, then we can definitely use AMGM somehow. So let's use the AMGM on the numerator. So consider the numerator. What is the geometric mean of these two terms? Well, that would be the square root of x times 3 to the x times x squared minus 4x. And by AMGM, this geometric mean is always smaller or equal to the arithmetic mean, which is 3 to the x times x squared minus 4x, and then plus x divided by 2, their average. Now, here, after we collect the like terms, admittedly, there's not much else that we can do. I mean, sure, maybe we can, I don't know, factor out the x and maybe do some canceling. I don't know. But altogether, this isn't all that useful. Now, here is a key problem-solving strategy. Wishful thinking. Think about what you want to be true, and maybe make that happen. That might make no sense, but in this problem, it works out very nicely. If we instead had 4x instead of x itself, then when we take the arithmetic mean, that would be negative 4x plus 4x, and that would cancel out, leaving just 3 to the x times x squared. So if this x was instead 4x, then that would be much better. But this is x, and that's that. We can't change that. Or can we? Now, this is where things get cool. If we had instead 4x here, meaning we multiply the numerator by 4 to get a 4x there, we suddenly get our desired expression. When we take the arithmetic mean, the negative 4x and the 4x cancel out. But you can't just multiply by 4 for no reason. You can't just do it for free. You have to multiply the entire expression by 1 over 4 to maintain the equality, right? Otherwise, you'll lose the balance, and that's not how math works. So, now that we've gotten a desired form on the top, whilst maintaining the same expression, now let's apply AMGM on the top. Then the geometric mean is square root of 3 to the x times x squared minus 4x times 4x now. This is by the inequality smaller or equal to. Now take the average, then this and this would cancel out, so you get 3 to the x times x squared over 2. And now we may square both sides. So we would have 3 to the x times x squared minus 4x, and then all times 4x. This is smaller or equal to 3 to the 2x times x to the 4 divided by 4. And note we can square both sides because both sides are positive. So now this is the numerator of our expression. Now to get our expression, all we need to do is divide both sides of the inequality by the denominator, right? 3 to the 2x times x to the 4, and then multiply the entire thing by 1/4. So now let's check this out. If we were to divide both sides by 3 to the 2x times x to the 4, right? And we can do this because this blue expression is positive. Then we basically are left almost with the same expression, right? This is almost the same as this. We just need to multiply both sides by 1/4. And there you have it. On this side, we have our original expression, and this is smaller or equal to some other expression. Now, whatever it's smaller or equal to has to be the maximum, right? So now let's simplify the right-hand side. Firstly, we notice that 3 to the 2x times x to the 4. This cancels out with this 3 to the 2x times x to the 4 on top. So these two actually just cancel away. So over here, you would just get this expression here is equal to 1/4 times 1/4. And this is 1 over 16. Great, a constant. This led us to a constant value. And over here, this inequality is telling us that our original expression, right? Our original expression we were trying to maximize. This original expression is smaller or equal to 1 over 16. Now, there's one more obstacle we have to get over with before we can say that this is our maximum. Firstly, this notation, smaller or equal to, basically is just saying that this expression is always smaller or equal to 1 over 16. But it doesn't necessarily mean that it's able to achieve 1 over 16. So if this is always smaller than 1 over 16 but can never reach 1 over 16, then this notation is still perfectly valid. Therefore, we actually have to show that it is possible in order to achieve 1 over 16 with this expression. How do we do that? Well, that will be left as an exercise to you. And if you're not familiar with how to do this, then I will present you another fact about AMGM. So, consider this. There's an inequality symbol, right? But this becomes an equal sign if and only if, so it becomes equal if and only if, which I'll write like this, if and only if A is equal to B. And that's the equality condition. It is absolutely necessary. It's an if and only if condition. Therefore, I want you to try to use this condition to show that it is indeed possible to reach 1 over 16 with this expression. If you do that, then you're done, because if it's smaller or equal to 1 over 16, and it's able to achieve 1 over 16, then obviously 1 over 16 is indeed the maximum value. So that's how you can do it. Try it for yourself. I hope you learned a lot from this video. I hope you found this interesting. If you did, then please do consider dropping a like and subscribing. Thank you very much.